Thank you, everyone, for joining. This is Tamal. He is a student at Macquarie and visiting us for the day. Tamal is giving a colloquium at RSA under the ASA ECR colloquium series. He works on high-redshift galaxies and he studies them using VLT and Muse data. He's going to talk to us about our research. Take it away, Tamal.
Thank you. Can I use this?
You don't need that.
Yeah, you don't. Yeah. I mean,
You don't need it.
Can you try it? Hello. Yeah. Okay. Thanks, everyone. Thanks very much for hosting me and giving me the opportunity to come and present at this beautiful place. I am Tamal Mukherjee, a second-year PhD student at Macquarie University. So I'm working with two amazing supervisors, Dr. Tayyab Azafar and Dr. Timia Nanakara from Swinburne. Today I'm going to talk about how we can use Lyman-alpha emissions to probe galaxy kinematics and the epoch of reionization. Okay, so let's start with a basic picture of the universe. We all know that approximately 70% of the universe's content is dark energy and the rest is matter, out of which 25% is dark matter and the rest is atomic matter. Now, within this atomic matter, 75% is hydrogen and the rest are helium and other elements. So you can see from the 75%, due to its prevalence throughout the universe, due to the prevalence of hydrogen throughout the universe, the lines associated with hydrogen are, excellent probe to study the universe. For example, we know the series of transition in hydrogen atom. For example, first excited state to ground state transition is known as Lyman-alpha transition with a raised wavelength of 1215 angstrom. And the next one is second excited state to first excited state transition, which is known as Balmer-alpha or H-alpha transition. So in this talk, we will mainly focus on Lyman-alpha transition. Now let's understand when an hydrogen atom emits Lyman-alpha photons. So there are basically two mechanisms that can lead to Lyman-alpha photons emission. First one is collisional excitation. So when a free electron collides with a hydrogen atom, it leaves the electron of the hydrogen atom in an excited state, and then it radiatively cascades down to the ground state and it emits Lyman-alpha photons. So we also call it as cooling radiation because it cools down the gas temperature. The next one is recombination. When an electron and proton recombine to form a hydrogen atom, it also leaves the electron to an excited state, and when it cascades down to the ground state, it leads to Lyman-alpha photon emission. Now, given those two Lyman-alpha emission mechanism, let's understand what are the origins of Lyman-alpha emission in the universe. So Lyman-alpha photons are basically emitted by star-forming galaxies, which are known as Lyman-alpha emitters or Lyman-alpha emitting galaxies. So there are basically two regions that emit Lyman-alpha photons in a galaxy. First one is interstellar medium. There, we can see that the star-forming regions that makes the ionized hydrogen, that can lead to Lyman-alpha photon emission by the process of recombination that I mentioned earlier. The other process is if there is any nuclear activities going on in the galaxy, for example, AGN, that can also lead to a broad Lyman-alpha profile. The other one is CGM or circumgalactic medium to outer halo, where you can see the outflowing gas from the galaxy that can sometimes collisionally excite the hydrogen atom to emit Lyman-alpha photons. The other one is cooling radiation from cold accretion. So in the galaxy, sometimes it gets cold gas from outside, and it also excites the hydrogen atom to leak Lyman-alpha photons. The other one is fluorescence emission or high excitation emission produced by halo that can also create Lyman-alpha photons. Now, this talk is mainly focused on how we can use Lyman-alpha as a tracer of CGM gas kinematics And the next part will be how we can use Lyman-alpha emitters to study the epoch of reionization. Now, in this regard, I have been using Macquarie data, which is a VLT-Muse large program, primarily working on this visible wavelength range of the electromagnetic spectrum. And it has been doing a remarkable work, by providing spatially resolved spectroscopy of star and gas in galaxies with a decent amount of spatial resolution. So thanks to the Macquarie team for giving me the opportunity to work with this amazing data. As you can see, within using Macquarie data, I have been basically targeting Lyman-alpha emitting galaxies at a redshift from 2.9 to 6.6. So basically, at the end of reionization up to the cosmic noon or the peak of star formation. So using Macquarie data, we found around 370 Lyman-alpha emitting galaxies. And you can see in this plot the number count of Lyman-alpha emitters as a function of luminosity, while we compare our work with the Muse deep observations. And you can clearly see that we are mainly focusing on our data will lead to study the Lyman-alpha at a higher luminosity range, mid to high luminosity range. Also, you can see in this luminosity function, luminosity plot as a function of redshift, and you can also clearly see that these red circles are our Macquarie LAs, and we are basically probing these higher luminosity regions up to redshift 6.6. So now I am entering to the first part of the talk, which is probing CGM gas kinematics using Lyman-alpha emission. So we know that Lyman-alpha is a resonant ion. So basically it gets scattered by the neutral hydrogen gas that is present in the interstellar medium, in the circumgalactic medium, and in the intergalactic medium. So the Lyman-alpha photon is getting scattered and diffused in both real and frequency space. And that's why we get a spatially extended Lyman-alpha and a spectrally extended Lyman-alpha or spectrally skewed Lyman-alpha. Now, these observations of Lyman-alpha basically identify the photons that are coming from the photons that are coming from those scattering of hydrogen gas that is in the surrounding. So we are basically missing the information about the original source of Lyman-alpha that is emitting Lyman-alpha photons. Instead, we are probing the distribution or kinematics of CGM and IgM gas from where the Lyman-alpha is getting scattered. You can see here some examples of extended Lyman-alpha emission. In the left plot, you can see the Lyman-alpha halo surrounding galaxies in the Muse Hubble Ultra-Deep Field Survey. In the middle plot, you can see a giant Lyman-alpha blob, which is like extended up to 100 kiloparsec at a redshift of 3.1. And on the right one, you can see a stream of ionized Lyman-alpha or a filamentary emission of Lyman-alpha, which is again extended up to 100 of kiloparsec. Now let's understand the scattering effect of Lyman-alpha photons. So this is basically a joint observation of Lyman-alpha and H-alpha from a galaxy at a redshift of 2 to 3 from the Hashimoto et al. Where you can see, we know that H-alpha is a non-resonant line, so they are not scattering. Again, H-alpha is produced by the same recombination process by which Lyman-alpha is produced. But the thing is, as H-alpha is not scattering, they will indicate the exact shape of Lyman-alpha, like how should the Lyman-alpha line look like if they are not scattering. So you can see here that it clearly shows that the Lyman-alpha lines are getting redshifted as compared to the systemic velocity that is probed by the H-alpha. And so there are basically two effects of scattering. One is Lyman-alpha is getting redshifted, and the other is, you can see, there is a sharp edge in the bluer side of the Lyman-alpha, which is basically the effect of IgM scattering in the Lyman-alpha photons. Now understand how the Lyman-alpha line profile looks like from the galaxies. So there is a basic picture. So we often found that Lyman-alpha lines are often redshifted, and we get a single red skewed profile. And also we get multiple stellar, low ionization stellar absorption lines, which are found to be blue shifted. And you can see that this is the feature, which is a red skewed profile of Lyman-alpha. So this is basically suggesting that Lyman-alpha is scattered to us from the far end of the nebular regions, from where these low ionization stellar absorption lines we can see. So as an example, you can see in the Macquarie data, we also found the similar thing where a great Lyman-alpha profile, a very bright Lyman-alpha is rate shifted from the systemic velocity, and also it is a rate skewed line. Now, we also found some interesting double peak profile of Lyman-alpha emitters, and we will see how these are so interesting. So when gas is outflowing from the galaxy, we see a profile with dominant red peak, which is on the top. And when gas is inflowing onto the galaxy or gas is falling onto the galaxy, we see a dominant blue peak in the spectra. Now, the interesting fact is only 0.35% of the overall Lyman-alpha emitter population are blue dominated. But we know that galaxies are forming by, accreting materials from the outside. But still we are getting only a few, like 0.35% of the blue dominated regions, which is indicating inflows. So that basically makes a unique laboratory to study gas accretion processes in the galaxies, where you can see some great examples of blue dominated profiles detected in the left. You can see it's a Lyman-alpha blob, where they see a particular region which is showing the blue dominant profile. In this plot, you can see a laced galaxy where they observed blue dominant profile. And on the bottom panel, you can see that this is the UV brightest galaxy where they observed a blue dominant profile. And also they observed an infalling stream of gas. Now, using Macquarie data, we found only 3 out of 370 Lyman-alpha emitters that is leaking blue peak emission in the Lyman-alpha. So this is one of the examples where you can see a giant Lyman-alpha halo surrounding these 3 galaxies, which are all at same redshift, 2.9. This galaxy, which is at the center, is the UV brightest among these 3, and other 3 are fainter than this. And you can see on the right plot, which is the Lyman-alpha narrowband, where you can see at the location of this UV brightest galaxy, you can see multiple stellar absorption features, and also absorption in Lyman-alpha. While these 2 regions are showing maximum surface brightness in Lyman-alpha, so interestingly, we found that the main region of surface bright Lyman-alpha is showing a strong blue peak there. So basically, gas is falling onto the galaxy in these 2 regions. So in order to quantify the regions of blue and red dominated regions, we study the spatially resolved map of flux ratio, which is on the right, where you can clearly see the regions of blue and red dominated regions in the narrowband. And you can see that this is the absorption, and surrounding this, you can see outflows. Now, we also see in the region of absorption, multiple stellar absorption features, very strong, which is indicating that this region or this galaxy is quite evolved. And this is metal enriched as well, which is leaking gas or which is outflowing gas and triggering star formation mainly in these 2 regions. We also found some other examples of blue dominated Lyman-alpha halo in the Macquarie data, which is, you can see it's a redshift of 3.6, where you can even see multiple locations of Lyman-alpha, bright regions of Lyman-alpha, and also multiple locations of blue dominated regions. So basically indicating there are multiple regions that is accreting gas within a halo. Now, there is another example at a redshift 4.8, quite high redshift, which is a compact Lyman-alpha emitter, but still showing a blue dominant Lyman-alpha profile. On the right plot, you can see the peak separation map, spatially resolved, pixel by pixel map of peak separation. And you can see the peak separation is very high at the center, while it is gradually decreasing when we go to the outskirts. So basically this peak separation, we will see later, this is basically mapping the neutral hydrogen present in the galaxy. So now the question is, what causes this blue dominant peak in Lyman-alpha? The answer is simple, gas accretion onto the galaxies. But the question is, which type of accretion are these? So there are several modes of gas accretion we can consider. First one is cold, pristine gas that is falling into the galaxy from cosmic wave, which is a cold filament of neutral hydrogen gas, which is often metal poor, and that can trigger star formation. The other scenario is recycled accretion. So when a galaxy is outflowing gas by stellar feedback or some other process, if the gas is so they are basically outflowing gas to the CGM, into the CGM. And if this gas fails to escape the CGM, this again falls back to the galaxy and again triggers star formation. So this is called recycled accretion, which is found to be metal-enriched gas. And this can also show a blue dominant profile. The other possibility would be accretion due to mergers or interactions that we see on the first one, where these three galaxies are basically interacting by inflowing and outflowing gases. Now, the conclusion is we don't yet know which is the dominant mechanism on those three galaxies, and we need further spectroscopy. For example, we need spatially resolved H-alpha and other race optical emission lines to confirm the exact accretion scenario in these galaxies. Now, understanding all those scattering effects, let's try to understand the radiative transfer of Lyman-alpha. So we basically use a simple cell model where there is a Lyman-alpha source at the center, and there is a homogeneous isothermal spherical cell surrounding the Lyman-alpha source. And you can see there are a couple of source parameters. There are two source parameters, which are the line width of the full width hub maximum of the Lyman-alpha line, or the strength or the equivalent width of the Lyman-alpha line. And there are a couple of parameters for the cell, which are from this model, from Varahmetial. There are parameters like neutral hydrogen column density, the cell velocity, the expansion velocity of the cell, the dust optical depth, and the impact parameter. Now we use a Python-based Lyman-alpha radiative transfer code called Zelda to model our double-peak Lyman-alpha profiles that we found in Macquarie data. So basically we have 5 phi parameters, which are expansion velocity of the cell, neutral hydrogen column density, dust optical depth, intrinsic equivalent width of the Lyman-alpha, and the intrinsic line width of Lyman-alpha. So basically we are running the Monte Carlo simulations on like different values of only these 3 parameters, is cell velocity, column density, and dust optical depth. And by running the Monte Carlo simulations, we are generating profiles with different equivalent widths and line widths via post-processing. So here you can see one example of one Macquarie double peak LAE at a redshift of 3.69, which is an excellent one with, you can see a very high signal to noise. And you can see the power of Zelda. It is exactly fitting the observed profile very accurately. And also you can see the wellness of the fit from the correlation plot on the right. So let's try to understand how these observed Lyman-alpha parameters are correlated with the fitting parameters that we generate using the Zelda. Here you can see the observed parameter, which is blue to red flux ratio, how it is correlated with the cell velocity, which is a fitted parameter. You can see there is a clear anti-correlation between these two. And you can see that when the blue flux is higher, the cell velocity is lower, which is in the other words, basically when the outflow velocity is low or inflow velocity is high, we get high flux in the blue that I said earlier as well. Now, there is another thing which is like how we can coordinate the peak separation, double peak separation with the neutral hydrogen column density that is present on the galaxy. So you can see this Varahmetial paper where they found a nice correlation between the peak separation and the neutral hydrogen column density. But this work was at a redshift of 0.3 to 1.2. So these are basically local galaxies. So we are extending the same work using Macquarie data to a high redshift of 2.9 to 5.1 for the first time. And we found a similar kind of correlation, you can see. So you can see that when the peak separation, if separation is low, the column density is very low. What does that signify? So smaller peak separation is basically leading to low column density channels, which can indicate that this low column density channel can indeed leak Lyman continuum or ionizing photons. So basically, that is the power of double peak Lyman-alpha spectra. We can use double peak Lyman-alpha spectra. We can model them, and from the observed and the model fit parameters, we can actually study the amount of neutral hydrogen that is present on the galaxy, and we can eventually get an indication of Lyman continuum escape from these galaxies. Now move on to the next part of the talk, which is how we can use Lyman-alpha photons to study epoch of reionization. So using Lyman-alpha photons, we can basically probe galaxies up to the cosmic dawn, up to redshift of 14, 15. So you can see in this plot, we are basically getting Lyman-alpha from here the Lyman-alpha is the number count is very high and it's getting lower and we get up to redshift of 14. Using this plot, you can see this is the farthest galaxy we found using the jet spectroscopy, which is at a redshift of 14.32 using this Lyman break technique. So you can see this using Lyman-alpha photons, using Lyman-alpha spectra, we can probe galaxies deep into the epoch of reionization. Now let's understand how IgM neutral fraction affects the Lyman-alpha transmission. On the left plot, you can see the IgM neutral fraction as a function of redshift and how is it is varying. See here at a redshift of 5.5, it's becoming 0. That means universe is becoming completely ionized. And it's gradually increasing, and at a redshift of 9 or 10, you can see it's completely neutral. And on the right plot, you can see the Lyman-alpha transmission as a function of redshift. You can see that at a redshift of 6, 7, the transmission is higher. And as we go to high redshift, the Lyman-alpha transmission is getting down because of the increasing the neutral fraction of the intergalactic medium. So from this plot, you can see this region is very important, 5.5 to 6.6. So this is basically the transition region of the universe, where the universe is getting fully ionized, fully neutral to getting fully ionized. So we study Lyman-alpha emitting galaxies in this region of redshift 5.5 to 6.6 to understand the effect of IgM transmission. So we found 22 Lyman-alpha emitters in this redshift range, and you can see 3 examples of that at a redshift of 5.65, at a redshift of 6.1, and at a redshift of 5.6. And so you can see these profiles are not single like normal Gaussian. This is red skewed. So we use an asymmetric Gaussian fitting using a function like this to fit those Lyman-alpha profiles and extract the parameters, for example, the line widths and the equivalent widths. So the line widths can be calculated using these parameters, for example, W and the asymmetry parameters, so the W basically deciding, so both of these parameters are deciding the full width or the line width of the Lyman-alpha. So now, after calculating the line widths and the properties, we study how the Lyman-alpha line widths change with luminosity. You can see at a redshift of 5.5 to 6, there is almost no evolution of Lyman-alpha line width as a function of luminosity. But if we go to the redshift regime of 6 to 7, you can clearly see that low luminosity LAs are having low line widths, and the high luminosity LAs are having higher line widths. Why is this so? So we assume that these LAs, which are showing high luminosity and higher line widths, they are basically residing in larger ionized bubble. So if they are residing in larger ionized bubble, they are allowing most of the Lyman-alpha photons to leak through this ionized region. And that is basically, so they are basically avoiding the effects of IgM scattering. Now, in order to quantify the size of bubbles, we use some method. So we solve the evolution equation of ionizing front and arrive at an equation of the bubble radius. And we use some fiducial value of the Lyman continuum escape of 5%, and the age, where the T age is basically the time since which the Lyman continuum photons or the ionizing photons is switched on the particular galaxy, which we take as 100 million years. Now you can see how bubble radius change as a function of this TH for different values of Lyman continuum escape fraction. And you can see that, for example, at an age of 60 and at a continuum escape fraction of 10%, which is equivalent to at an age of as an age of 100 million year. So basically 60 and 10% is exactly similar to 120 at 5%. So there is a degeneracy between these two parameters, the Lyman continuum escape fraction and the TH. So using this model, we are calculating the bubble radius for our 22 Lyman-alpha emitters, and we found that there is a significant correlation between the bubble radius and the line width of Lyman-alpha. So that is again suggesting that these high luminosity or high line width LAs are sitting inside the larger ionized bubbles. Also, we found that our Lyman-alpha emitters are UV bright. So we use hyper supreme cams over white layer data, and we use their Y-band magnitudes to calculate the UV bright, MUV, raised frame UV magnitudes, and we found they are very high. We call them UV bright galaxies. And here you can see how IgM transmission and bubble size are correlated as a function of velocity offset, and even as a function of this UV magnitude. On the left plot, you can see if the galaxies are when the galaxies are UV bright, it is getting higher transmission as compared to when the galaxies are UV faint. Also in the right plot, you can see it also depends on the velocity offset. So at what velocities Lyman-alpha photons are getting leaked. So if the velocity offsets are higher, you can also see that they are residing on the larger bubbles with very high IgM transmission of Lyman-alpha photons. So this is the final picture where you can understand how these UV bright galaxies are creating bubbles around them and leaking Lyman-alpha photons. So this side is basically during the epoch of reionization, where you can see that UV faint galaxies have lower bubble size, and you can get like faint Lyman-alpha from them. Whereas in the case of UV bright galaxies, where the bubble size is very large, and you can get Lyman-alpha from those UV bright galaxies very easily with very broad lines and very high equivalent width. Also, there are some things like surrounding these UV bright galaxies, there can be many faint sources as well, which is also contributing to the bubble sizes. But we don't yet know using MACPI data that what are the other faint sources at the same redshift. So we need further infrared spectroscopy. We also found another interesting thing, which is clustering of LA at a very high redshift of 6.046, where you can see these two LAs are just separated by almost 15.92 kiloparsec only. So this kind of clustering of LA at the end of reionization basically increased the bubble size. And when it increased the bubble size, it is also increasing the IgM transmission. So that is allowing most of the Lyman-alpha photons to leak from those galaxies. So it will basically give an idea of a big picture where how the reionization progresses in the universe. So it's basically highlighting a patchy reionization scenario where there are different UV bright galaxies, they are getting clustered and forming some regions of bubbles. And at a redshift of 5 or 5.5, these bubbles are basically overlapping to make a fully reionized universe. Okay, so that is the summary. So what we studied, first we studied that we discovered some blue-dominated Lyman-alpha, which are very interesting, that are basically tracing CGM gas inflows and a unique laboratory to study accretion processes in the galaxies. The next one is we modeled the observed Lyman-alpha line profiles using the radiative transfer model, and we also incorporated a homogeneous cell model, and we found that how the peak ratios are correlated with the outflow or expansion velocity of the cell. And we also investigate how the double peak separation is correlated with the neutral hydrogen column density, which is a possible indication of Lyman continuum escape from those galaxies. And finally, we studied the evolution of Lyman-alpha line width with luminosity during the epoch of reionization, and we found that the high luminosity LAs at a redshift greater than 6 are located inside the larger ionized bubbles, and that's why we are getting maximum maximum Lyman-alpha transmission, which is showing a broader line profiles. That's all for today. Thank you.
Thank you for the talk, Tamal.
Yeah.
We can take questions now. Since Yushan asked in the middle of the talk, Yushan, can you unmute yourself and ask the question, or do you want me to read it out?
Of course. So it's just, I remember at the beginning you showed a couple of examples with strong blue emission, and they're actually higher than your red side. But when you show the ratio between the flux of the blue versus the red as a function of velocity, you don't actually see any points that's above 1. So I was just wondering if this is because of the prior for your model that you are not actually allowing negative velocity, or if you have any other comments on.
Sorry, I missed in between. So can you repeat? Let me go to the plot.
I think lower.
Yeah. Yeah. Can you repeat the question?
So if you go to the plot where you show the ratio between the blue flux
Yeah.
to the red flux
Yeah.
as a function of your fitted velocity,
Mhm.
yeah, it's easier to use that plot to explain my question.
It's I think he's talking about the plot in which you show the flux ratio as a function of velocity.
Oh, okay.
Yeah.
Yeah, right?
Yeah. So because you have a couple of blue emitters, so you should have some plots with the ratio.
Oh, no. So yeah, I got you. So this one is only for the double peak with strong rate peak profile, so which are outflows. We are not able to fit we are unable to fit the inflow profiles, like our models is not able to fit the inflows yet. So these are all outflows. So that's why you can see the blue to red flux ratio never crossing 1. So these are all outflows profile.
Yes. Yeah.
Or the red dominated profiles.
So I would naively expecting the model can deal with negative velocity, so that the outflow will become inflow. So you can also fit it.
Yeah. So the problem is, it doesn't have enough training of those inflow, as these are rare. So we need many trainings sets to train the model with inflows. Then only it will be able to fit the inflows.
Thanks.
Thank you for a very nice talk. So I was just wondering, the first part with inflows and outflows, there are also probably random flow, the turbulent flow, right?
Yeah.
How does that change the profile?
That is, we don't know. So basically, we only see the blue dominant profiles. We can locate the regions of that, but we can't say from where the exact gas accretion is happening. For example, if you go to that plot, yeah. So using this map, you can see that these are the blue dominated regions and these are the red dominated regions. Basically, so red dominated regions are showing the outflows and the blue dominated regions are showing the inflows, but we don't yet know what is the exact mechanism. Whether it's, as I told before, that it can be a crystalline gas from cosmic wave, it can be a recycle accretion or something like that, or any turbulence is going on. So we don't yet know.
Yeah, thank you.
Any other question for Tamal?
So I also have a question about that. So can this be an inclined, volcanical outflow, so part of the gas towards us?
Yeah, it's exactly a Doppler effect, simple Doppler. So when a gas is outflowing from the galaxy, we are getting a red dominated profile. When a gas is falling, we are getting a blue dominated profile.
So and also can part of the emission from the diffuse gas halo around galaxies is ionized by the alpha?
Yeah.
So another one is that, so you model that double peak profile with some models. So does any of those parameters show any concentration?
We haven't studied yet. I don't think so. You can also calculate the escape fraction. That will evolve with redshift, I believe. But I don't think so other parameters will evolve. As we can see for this plot, Yeah. So this one is at a redshift of 3.3 to 1.2 for local galaxies. And we can see a similar kind of behavior for high redshift galaxies as well. So the mechanism is almost same. But what I added is like I said that smaller peak separation is showing that it can be a low column density channels that can leak Lyman continuum photons. But this may not always hold true because for high redshift Lyman continuum leakers, the mechanism can be different. Just not like low column density channel leaking Lyman continuum. There can be other mechanism that can leak Lyman continuum. So yeah, we don't yet know what is the exact mechanism for Lyman continuum emitting. But as part of the redshift evolution, you can see that it's almost similar.
Yushan, you had another question? Yushan, did you want to ask your question or?
Yeah, sorry, I forgot to unmute myself. So I don't really understand the arguments on the outflow types and why this is important to determine the blue side emission. Can you explain why different types of emission, different types of outflow matters when you determine the blue side emission?
So you are asking about blue dominant emission and outflow, right?
Yeah, because you were trying to, I think you were trying to promote the idea that different types of outflow matters in terms of the blue side emission. In terms of modeling the blue side emission.
Blue side emission is only for the inflows, not for the outflows. So when we have a blue dominant in the sense when the blue flux is higher than the red flux, that means there is a significant inflows, not the outflows. While on the other hand, when the red flux is higher, then there is outflows.
Yeah. So, well, in that sense, I rephrase my question. So why does different types of outflow matters in terms of modeling the red side?
Yushan wants to know if the different kinds of outflows would mean different ways of modeling the red side. Is that what you're asking, Yushan?
Different kind of outflows means the different mechanism of outflows you are talking about?
Yeah, I think you spoke about how it would be.
Yeah, so I know. So the model is generally based on just the profile. It's not depend on the exact mechanism of outflow. So what we have an observed profile and we are trying to model it using something. So I don't think so. We usually incorporate the exact mechanism of outflows from there, but it's just reproducing the observed profile with some models.
Yeah, exactly. Most models just assume an outflow shell simple modeling. So that's why I got confused when you try to explain different types of outflow. Okay, thanks.
Yeah. So basically, as I told that there is a central Lyman-alpha source and there is a cell. That cell is basically outflowing. So that's the mechanism. So this V expansion velocity is like positive, and as you were mentioning that if you change it to some negative value, it can generate inflow. So it's something like that. So it doesn't exactly probe the exact mechanism of inflows or outflows. So it's more like reproducing the spectra, reproducing the observed spectra with some model. So it's just basically, give some idea of the amount of neutral hydrogen present in the surrounding medium.
Okay, thanks.
Ralph?
Oh, thank you for a good, wonderful talk. You showed some objects early on that were clearly highly non-spherical in Lyman-alpha. And as you know, Lyman-alpha can scatter anything from a few to 100 million times before it escapes any ionized. How do you account for looking the orientation of any AGN and looking down directly at a blazar, for example, you may see blue shifted Lyman-alpha in an outflow towards you because the dust is destroyed and it's free to escape. It's not a sphere at all. Do you expect orientation and non-spherical geometry to have a big effect on your conclusions or not?
Yeah, so what I know is that there are models that try to understand the origin of blue peak emission using the impact parameter and the line of sight velocity. So what they found is that it's often found that when the line of it's often found that when the Lyman-alpha is emitting like from the age-on galaxy, it is often blue dominated as compared to a face-on galaxy. So yeah, it's true that there is an effect of the line of sight on the spectra, but with the current data, we can't actually do that thing. So yeah, maybe we need a better modeling to do that.
Okay, and one just quick one. When you have those red side only emitters, and you know the blue side has been absorbed or destroyed by dust or turned into photon emission, why don't you just assume it's symmetrical using the red half and measure the virtual size of the line, assuming a Gaussian fitted just on the red half rather than a complicated function?
You mean for the double peak one or the single peak for during the Riemann?
Towards the end of your talk, you showed some red only lines, and why would it make a lot of difference to just assume you're seeing half of the Gaussian and fit a Gaussian with just the red half that you see? Is that all? Is that what that says? I can't read.
Yeah.
My vision is failing.
So the only idea to fit with an asymmetric Gaussian is because, you know, in high redshift, the bluer side is getting affected, like getting steeper by the IgM absorption. So if we try to fit with a normal Gaussian, it won't fit very well. So that's the idea of implementing asymmetric Gaussian fitting there.
Yeah, but if you remove the blue half all completely and just fit the partial Gaussian to the red with the Marmquart-Liebenberg, it should still find a Gaussian where the part is.
Oh, you mean like a Gaussian like this?
Yeah.
Right? Yeah.
Would that make any difference?
So the whole motivation is to understand the observed equivalent width and the full width half maxima.
Yes.
So I think if we fit it like this with a full normal Gaussian, we are overestimating the flux and the line width as well.
But the blue cutoff is different in each case because of each different object is missing more or less of the Gaussian, whereas the far red is a pure sample of the actual width of the Lyman-alpha. Anyway, just a suggestion to explore. Thank you for
so I got you. So if we have, so for example, we don't have the systemic velocity, we don't have H-alpha or other emission line observation in Macquarie. So we don't know the exact velocity offset of Lyman-alpha as compared to the systemic. And again, that's the reason we don't know the exact velocity where the Lyman-alpha is leaking. So we don't yet quantify the exact IgM absorption on those Lyman-alpha emitters. So that's we can't do that.
Okay.
And that's why we are fitting with the asymmetric Gaussian.
Okay, thank you very much.
Any other questions for Tamal? Online? If not, we can thank Tamal once more. He is here for the whole day. If you would like to chat with him, he's sitting in one of the hot desks in Woolley building. We'll be taking Tamal for lunch at about noon. If you're interested to join, you can come here right in the lobby at noon. And this is a bottle of wine for you, Tamal, from Brian Schmidt's Winery.
Thank
you again.